So coming to the AVL trees, AVL tree, it is also the property of the, the binary search tree. Whatever the properties of the binary search tree, the same thing is to be included within the AVL tree. And the additional property that is involved in the AVL tree is the balance factor, or we can say like a self-balanced tree. So within the case of the self-balanced tree, whenever you are adding the new node or whenever you are deleting certain kind of the node in the existing tree, and by this insertion and deletion, if the tree becomes unbalanced, then we need to convert this kind of the unbalanced tree to the balanced tree. And in the previous video, that is AVL tree single rotations are being taken into the consideration. That is, whenever you consider about the AVL tree, you need to also look into the concept of the balance factor. So the balance factor, like take for example here given certain kind of the binary search tree, and you have to find the balance factor of this kind of the every node that is present in the binary search tree. So basically we start from the leaf nodes. The leaf node of the balance factor of the leaf node will be equal to 0, and coming to this kind of the parent node, and this node, that is height of the left subtree, that is 1, minus height of the right subtree, that is 1. That will be equal to 1 minus 1, that is equal to 0. And here in this case, that is the height of the left subtree will be equal to 1, minus height of the right subtree is equal to 0. So 1 minus 0, that will be equal to 1. And when coming to the root node, height of your left subtree, that is equal to 2, minus height of the right subtree, that is equal to 2. So 0. And we have studied the AVL tree, the balance factor, which ranges from 0 to 1. Minus 1 to 1. That is, B can have, that is minus 1, and balance factor can have 0, and balance factor can have, that is 1. These are the allowable values of the balance factor for every kind of the node in the AVL tree. And there may be certain kind of the scenario by adding a new node or by deleting a new node, by deleting an existing node, then it may become unbalanced. Unbalanced in the sense the balance factor exceeds these values. Like take for example, due to in certain kind of this scenario, this is your binary search tree, and the balance factor of this node will be equal to 0. Balance factor of this will be equal to 1 minus 0, that will be equal to 1. And balance factor of this will be equal to height of the left subtree, that is 2 minus 0, that will be equal to 2. So this is what we can say, it is unbalanced. Find the affected node, and you have to perform certain kind of the modifications, and those modifications which involves the rotations. So AVL rotations are being classified as a single rotation and the double rotations. And when considered about the single rotation, that is left rotations, that is denoted by LL rotation, right rotation denoted by RR rotation. And when considered about the double rotation, that is LR rotation, and as well as the RL rotations. That is in which scenarios we have to perform these rotations. So here the necessity for what is the necessity to rotate, that is a tree rotation is necessary when upon inserting a new node or deleting a node which leaves the tree in an unbalanced state. And what do you mean by the unbalanced state? That is beyond this kind of the values of the balance factor. That is the allowable balance factor values are minus 1, 0, 1. And if at any scenario by adding the new node, the balance factor of this kind of the node is beyond these values, then in such cases we can say it is an unbalanced state. When the tree is unbalanced state, you have to perform modifications. That is, you have to perform the rotations, and those rotations which includes single rotation and as well as the double rotation. So when to rotate, in which scenario you have to go for the single rotations, and in which scenario we have to go for the right rotation, double rotations. That is, if the tree is right heavy, check whether within the right heavy, if it is left heavy, then in such cases you have to perform the double left rotation. And similarly, if if this condition is the false condition, that is, if the tree's right subtree is not left heavy, that is, tree is right heavy, and whereas the tree's right subtree is not left heavy, that is, the else part will be executed. That is, perform single left rotation. That is, single rotation is being involved. What happens if the tree is not right heavy? Then it may be the left heavy. That is what we have said about the unbalanced state. Either it may be the left heavy or it may be the right heavy. If both the heights are same, we cannot say this is an unbalanced tree. So when the tree is left heavy, further once again, check whether within your left tree, if it is right heavy, then you need to perform the double right rotation, or which is also called as an LR rotation. And if this condition is the false condition, what does it mean? If the tree is left heavy and within your left subtree, right is not heavy, then in such cases, you need to perform the single right rotation. And that is what we can say about the concept of when to implement the rotations. That is, whenever you are by adding the new node or by deleting existing node, if the tree becomes unbalanced state, check these kinds of the conditions. Check whether tree is right heavy, and furthermore check whether it is left heavy. Then perform the double rotation. That is, RL rotation is to be implemented. And if the tree is right heavy and the left is not heavy, that is, if the tree's right subtree is not left heavy, then in such cases you have to perform the single rotation. And considering the example of the right heavy, we can give this diagram as an example of the right heavy. That is, if you look at this kind of the tree, that is, the root is K1, the right child is K2, and the right subtree is heavy. So right is heavy, and that is how we can say the tree is right heavy. And when you consider this scenario where left is heavy, so according to this tree diagram, you can observe left is heavy. That is, there is one more level as compared with the case of the right subtree. So left is heavy. Then in such cases, the else if it will be the true condition. And in which scenarios the tree's right subtree is left heavy, or in which scenario the tree's left subtree is right heavy. That will be discussed with this kind of this slide. That is, here you can observe when you look at this tree, you can say like right is heavy. Right is heavy. So if tree is right heavy, will be checked, and this condition is the true condition. If it is a true condition, furthermore check whether if it is left heavy. What does it means? Within your right tree, check whether it is left heavy. So left is heavy, because if you consider the B subtree and C subtree, it is one level more as compared with the D subtree. So we can say left is heavy. Then the second condition is also the true condition. That is, tree is right heavy and tree's right subtree and left is heavy. Then perform the double rotation. So observe in which scenarios the left rotation is to be implemented, right rotation is to be implemented, double rotations are to be implemented. Similarly, if you consider this tree diagram, that is, left is heavy because A, B, C are one more level as compared with the D, and out of which within your left subtree, right is heavy. So you need to perform the double rotations. So this is how you can understand when to perform the single rotation and when to perform the double rotations. If you consider this diagram related to the single rotation, that is, here you can observe B, consider B is the root, and we can say left is heavy. When left is heavy, you have to perform right rotation. rotate right. Here right is heavy and perform left rotation. When you are rotating left and when you are rotating right, there is a certain modifications which has to be done. Unlike in your previous route, the route will be updated. That is how we can say the single rotations. And take for example, you need to construct the AVL tree with the following keys, that is 20, 12, 24, 22 and so on. And later on you need to insert the node 40. Then in such cases, that is the property of the AVL tree says it should also be satisfy the property of the binary search tree, and the balance factor should be within the allowable range. That is, it can be either -1 or it can be a 0 or it can be either 1. So here whenever the first node is being inserted, that is node 20 is being inserted, and check the balance factor, because there is only one node and this will be the leaf node or the root node, and it becomes the balance factor will be equal to height of your the left subtree minus height of your the right subtree, which will be equal to 0. And when you are adding the next node, that is 12, that is here you need to add, you are inserting the node 20. Check the balance factor. Balance factor will be equal to 0, because no left subtree and no right subtree. 0 minus 0, that will be equal to 0. And when you are adding the next node, that is 12, so it AVL tree should satisfy the property of your the binary search tree. So where is this 12 has to be placed? 12 has to be placed within the left child of node 20. So when you are placing this node, as I mentioned, whenever you are adding the new node or whenever you are deleting the existing node, then in such cases you have to check the balance factor. The balance factor of the node 12 is, that is height of your the left subtree and height of your the right subtree, that is 0, and this balance factor will be updated. That is height of your the left subtree will be equal to 1 minus 0, that will be equal to 1. So this is allowed because the balance factor of node 20 is 1 and the balance factor of 12 is equal to 0. This is allowed. And that is how we can connect a node 20, the node 12 to the left child of your the node 20. And coming to the next part, that is you need to add the node 24. So where is this node 24 has to be placed? Check even before inserting the node 24 the balance factor. So here the balance factor of node 24 will be equal to 0, because the left subtree is equal to 0, right subtree equal to 0. The node 24 balance factor will be equal to 0. And coming to the next part, that is balance factor of the node 20. So node 20 balance factor, that is height of your the left subtree, that is 1, minus height of your the right subtree, that is equal to 1, so 0. So this is also within the permissible range of the balance factor. And we can connect node 24 to the right child of the node 20. Take the next node, that is node 22. And node 22, where actually the node 22 has to be placed to the left, because it traverses from the root. Node 22, it is greater than 20, so traverse towards to the right and compares with the existing node, that is 24. And what is the value that you are inserting? That is 22. So where this 22 has to be placed? To the left of, that is even before inserting the node, we are checking whether this is allowed or not by observing the balance factor. So node 22, if you are inserting, then the balance factor is being updated for every kind of your the node, because the new node is being updated. New node is being to be included. So balance factor of the leaf node is 0, and balance factor of this node 12, that is leaf node, is equal to 0. And coming to the node 24, the balance factor, that is height of your the left subtree, that is equal to 1, minus height of your the right subtree, that is equal to 0, that is equal to 1. This is allowed. So here you need to check the balance factor of the node 20. Height of your the left subtree, that is equal to 1, minus height of your the right subtree, that is equal to 2. So 1 minus 2, that will be equal to 1. So this is also within the given range of the balance factor. And that is how we can connect to the left of node 24. So node 22 is being connected to the left of the node 22. And how about the case of node 26? So it starts comparing with the root node. So 26. So 26 is the value that you want to node that you want to insert. And what is the value of your the root node that is present? That is 20. So it traverses towards to the right. It traverses towards to the right and checks the value of your the existing node, that is 24. What is the value that you need to insert? That is 26. So 26 is to be placed to the towards to the right of the node 24. When you are placing node 26 to the right of the 24, you have to check the balance factor of every node. What is the balance factor of the node 26? Since it is a leaf node, it will be equal to 0. Node 22, it will be equal to 0. Node 12, it will be equal to 0. And the balance factor of the node 24. The balance factor of the node 24, which is equal to height of your the left subtree, that is 1, minus height of your the right subtree, that will be equal to 1. So 0. And this is allowed within the balance factor range. And when considered about the node 20, so what is the height of your the left subtree? Height of the left subtree will be equal to 1 minus height of your the right subtree, that is 2. So 1 minus 2, that will be equal to minus 1. So this is also within the range of the possible values of your the balance factor. And hence we can insert node 26 to the right of 26 and take the next element. The next element, the next key node that is present is, that is 8. And so far we have inserted node 20, node 12, node 24, node 22, and similarly node 26 is been inserted. And the next level is you have to insert node 8. And when you need to insert the node 8, check the property of the binary search tree. So the node to be inserted is 8 and the root node is equal to 20. So it traverses towards to the left subtree. And the existing node, the current node will be equal to, that is 12. And what is the node that you want to insert? That is 8. So node 8 is placed towards to the left of the node 12. And compute the balance factor of every node. So when you compute the balance factor of every node, that is node 8 will be equal to 0, node 22 will be equal to 0, node 26 will be equal to 0, node 12 will be equal to 1 minus 0, that is 1, node 24, it is equal to 0, that is 1 minus 1, that will be equal to 0, node 20, that is left subtree, height of your the left subtree is 2, height of your the right subtree is equal to 2, that is 2 minus 2, that will be equal to 0. So all the nodes satisfy the property of your the binary searched, I mean the balance factor. And that is balance factor is either it may be 0 or 1 or minus 1. And what is the next node to be inserted? The next node to be inserted is equal to 30, where actually the 30 has to be placed. That is 30 has to be placed to the right child of the node 26, as I've explained the property of the binary search tree. That is, it starts from the root node. And what is the node to be inserted? That is 30 and compares with the root node, that is 20. So it traverses towards to the right, checks 24. The value that you want to insert is greater, so traverses towards to the right, checks the current node, that is 26, compares with the node to be inserted, that is 30. So 30 is greater, the node that you want to insert. So it is been placed as the right child of the node 26 and checks the balance factor. So the balance factor of node 30 is equal to 0 because it is a leaf node, node 22 0, node 8 0, and node 26 left subtree is equal to 0, right subtree is equal to 1. So 0 minus 1, that will be equal to minus 1. And node 24, height of your the left subtree is 1, height of your the right subtree is equal to 2. 1 minus 2, that will be equal to minus 1. And how about the node 12? That is left subtree is 1, right subtree is 0, that will be equal to 1. And node 20, the left subtree is equal to 2, the right subtree is equal to 3. So 2 minus 3, that will be equal to 1. So all the values of the balance factor of every kind of your node satisfies the property of the balance factor. And take the next value to be inserted, or the next node to be inserted. So when you are inserting the next node to be inserted, it starts comparing with the root node. That is, the next node to be inserted is, what is the next node? That is 21. So 21 has to be inserted. So when you are inserting the new node, that is 21, then starts comparing with the root value. That is 20 is present And what is the value present in the node to be inserted? That is 21. So it traverses towards the right and checks the current value, that is 24. And what is the node that is to be inserted? That is 21, and traverses towards the left. And the current node value is equal to 22. And what is the node that you want to insert? That is 21. And that is how it is being inserted to the left of the node 22. And compares the balance factor, that is, it computes the balance factor of every node. So node 21, it is equal to 0 because it is a leaf node. Node 30 equal to 0. Node 8, balance factor equal to 0. Node 22, balance factor equal to 1. Node 26, the balance factor will be equal to -1. Node 24, the balance factor will be equal to 2 minus 2, that is equal to 0. Node 12, the balance factor will be equal to 0 minus 1, 1 minus 0, that will be equal to 1. Node 20, the balance factor will be equal to height of your the left subtree, that is equal to 2, and the height of your the right subtree, which is equal to 3. So 2 minus 3, that is -1. So all the nodes satisfy the property of the balance factor. So far there is nothing modifications has to be done, no rotations are to be performed. And whenever the next node to be inserted, that is, here you can observe the next node to be added within the existing tree is 40. Starts comparing with the root node and traverses towards the right. The current node value is equal to 24 and the node to be inserted is 40. Traverses towards the right, checks the current node's value 26 and the node to be inserted, that is 40. So 40 is greater. So you have to traverse towards to the right, that is node 30, and checks the current value and the node to be inserted, that is 40, and traverses towards to the right, and the node is being placed. So by placing this kind of the node 40, you have to check the balance factor. So balance factor of node 40 is equal to 0 and 21 equal to 0, 8 equal to 0. And node 30, that is height of the left subtree is 0 minus height of the right subtree, that is 0 minus 1, that will be equal to -1. And node 26, that is height of the left subtree 0, height of the right subtree, that is 2, 0 minus 2, that will be equal to -2. This is how the node that is being affected, that is node 26. Identify the node that is being affected. The node that is being affected is 26. What do you mean by the affected node? That is beyond the balance factor range. That is, if you encounter which is not within the allowable range, -1, 0, 1, then we can say that node is being affected. So observe from that perspective, that is node 26. And how does this kind of the tree looks like, the subtree looks like? When you look at the perspective of the node 26, you observe right is heavy. Look from the perspective of the node that is being affected, that is 26. From this, identify how the tree looks like. That is, it is right heavy. If it is right heavy, then what should we perform? That is, rotate left. That is, when the tree is right heavy, when the tree is right heavy, then you need to perform rotate left. And when the tree is left heavy, of course, this is related to your single rotation. And when the tree is left heavy, then you need to rotate right. These are the concepts which has to be implemented. So tree is right heavy and you need to perform left rotation. So when you rotate left, when you rotate right, because it is right heavy, you need to rotate left. So when you rotate left, 30 becomes the root node, 26 becomes the left child, and 40 becomes the right child, and the remaining tree nodes are the same thing. That is 20, 12, 8 will be the same thing, 24, 22, 21 will be the same thing. And within your affected node and its respective subtree, there are certain changes. That is 30 becomes the root, 26 becomes the left child, and the 40 becomes the right child. This is how we can perform the rotate left and find the balance factor of every kind of the node. In the same fashion, if you need to insert the node 60, node 60 has been inserted as a root node, 52 has been placed as a left child. Find the balance factor, that is 0. 52 will be equal to 0, 60 will be equal to 1. It satisfies. Insert the next node, that is 70, to the right of the node 60. Check the balance factor, that is 52 will be equal to 0. Node 70, the balance factor will be equal to 0. Node 60, the balance factor will be equal to 0. And insert the next node, that is 44. So when you are inserting the next node, that is 44, check the balance factor. So it satisfies. Node 44, balance factor equal to 0. Node 52, balance factor will be equal to 1. Node 70, the balance factor will be equal to 0. Node 60, height of your the left subtree, that is 2, minus height of your the right subtree, that is 1. 2 minus 1, that will be equal to 1. It satisfies the property of your the AVL tree. And insert the next node, that is 58. Find the balance factor, no deviation. Insert the next node, that is 80. No deviation within your balance factor. And insert a node 56. So when you are inserting the node 56, try to find the balance factor. That is node 56, it is equal to 0. 58, it is equal to 1. 44, 0. Node 80, it is equal to 0. Node 52, it will be equal to 1 minus 2, that will be equal to minus 1. Node 70, 0 minus 1, that is minus 1. Node 60, that is 3 minus 2, that will be equal to 1. So the balance factor are within the allowable range. And when you are adding the next node, that is 54. So 54 is being placed towards to the left of the node 56 as per the property of the binary search tree. And when the node 54 is being inserted, check the balance factor, that is compute the balance factor of every node. So balance factor of node 54 is equal to 0. Node 80, it is equal to 0. Node 44, it is equal to 0. Node 56, 1. 58, 2. That is height of your the left subtree, that is 2, minus height of your the right subtree, that is equal to 0. So 2 minus 0, that will be equal to 2. This is not allowed, the balance factor, because the balance factor is minus 1, 0, 1. So the affected node is 58. And from this perspective, look that how does the subtree looks like. So the subtree is left is heavy. So when the tree is left heavy, what should be done? That is rotate right. Rotate right. When you are rotating right, root becomes 56, the left child becomes 54, the right child will be equal to 58. So when you are rotating right, the remaining nodes are unaffected, that is 60, 52, 44 is being placed as it is. 78 is also being placed as it is. And coming to this kind of the subtree which is being affected, there are certain rotations which are to be performed. That is rotate right, because left is heavy. When you rotate right, 56 becomes the root, left child will be equal to 54 and the right child will be equal to 58. And compute the balance factor of every kind of the node. That is, once you compute the balance factor of every kind of the node, you can observe it does not deviate any balance factor. The balance factor of all these kinds of the nodes will be equal to either it may be 1 or 0 or minus 1. And that is how we can say this is an AVL tree. What modification has been done? Find the affected node. From that perspective, check whether it is left heavy or right heavy. So far we are covering only the single rotations. So within your single rotation, you need to check whether it is left heavy or right heavy. If it is left heavy, then rotate right. And if it is right heavy, then you need to rotate left. So these are the possibilities if you need to perform the right rotation, left rotation, and so on. So coming to your LR rotation. So within the case of the double rotations, we can observe in your next video. So within the double rotations, if you recall about the the pseudocode related to when to perform the single rotation, when to perform the double rotations, and so on. So if the tree is left heavy, you need to rotate right. And if the tree is right heavy, then you need to rotate left. And upon rotation, there are certain modifications which have been done within your subtree. That is, your the root node is being changed the left child and as well as the right child is been affected. And when considering about the double rotations, so within the case of here the double rotations, in which scenario the double rotation has been involved? When the tree is left heavy and within which right is heavy. That is, if you consider the double rotation. So if you consider the double rotation, there is one possibility is left is heavy. We can give an example, left is heavy, by looking at this tree diagram. Left is heavy and out of which the right is heavy. Then in such cases, you have to perform the double rotation. That will be discussed in your next part. So far we have covered about the concept of how the AVL tree is been involved and what are the properties of the AVL tree. And in the next video, I will be covering about the double rotations. That is LR rotation and as well as the RL rotations. LR rotation, left is heavy, out of which the right subtree is heavy. And another double rotation, which is called as an RL rotation. So within the RL rotation, we can say right is heavy, out of which the left subtree is heavy. Then in such scenarios, you need to perform the RL rotations. And when you are considering about the LR rotations or the RL rotations, there are certain modifications which are to be done. That will be discussed in your next video.